Hi everybody, here is the quick confidence interval lesson that we did yesterday. That would have been Monday, January 25th, and also that we followed up with some examples today. I'm going to go back and talk about kind of the basic theory and the basic concept of this one more time, so in case you didn't get it the first time, you can take a look and take a listen to it this time. Okay, so the way I started was with this distribution. This is the distribution of our sample mean. Okay, now our sample mean is normally distributed as long as the conditions are true, and I think I told period 2 and I may have not told period 3 and 5 yet. There are actually two conditions. I only told you one of them last week. The first one is always going to be that we have a simple random sample, okay, and that's just going to be a condition that we'll have present throughout all of these things that we're going to be doing. Simple random sample. The second condition was the one that said if the population's normal, then X bar is normal. X bar is normal. And if you don't know, if population is unknown, then X bar is normal as long as N is big enough. And we'll clarify that in a couple of weeks. For now, that's all we need to know. So if these are true, then X bar is normally distributed, and we abbreviate that with the N. X bar has a mean of the population, which we call mu. It has a standard deviation of the standard deviation of the population over the square root of the sample size. Okay? And it looks like this. If we were to take lots and lots and lots of samples and find the means of all of those samples, that's kind of what we did in the computer lab the other day. 95% of those means would fall in this red region. Okay, now since X bar is normally distributed, how many standard deviations to the left and to the right of mu represents 95% of the observations? Yes, you're right. The empirical rule says this is going to be 2 standard deviations around the mean. Okay, now the empirical rule is really just an estimate. It's close. It's actually 1.96 standard deviations. 1.96 standard deviations around the mean. And then now you're saying, but wait, why is he writing sigma over square root of n? I thought sigma was standard deviation. Yeah, but we're talking about the standard deviation of the sample mean. That's this, okay? It depends on sigma of the population. But remember, when we have a sample mean, the distribution is a lot skinnier than the distribution of the population. Okay, so that's why we're looking at this. Almost 2 standard deviations to the right, almost 2 standard deviations to the left. Okay? So what I did in class was this. I said, you know what? I could take this quantity, and I'm going to go ahead and copy it, and I'm going to put it on this distribution. The boundaries of the red to the blue region on both sides can be represented by this quantity here. Take mu, subtract almost 2 standard deviations, take mu and add almost 2 standard deviations. Okay, pretty easy, right? You know the X bars you get will fall in the red region 95% of the time. 2.5% of the time they'll fall out here. The other 2.5% of the time they'll fall out on the other side, on the other blue region. Cool. So then we said, you know, let's take this one step further. Okay, and here's what I'm going to do. I'm going to get rid of my annotations, and I'm going to get rid of that, and we're going to do something else with it. I'm going to take this one, and I'm going to drop it on this distribution. Okay, guys, this is the important part. The X bars you get from lots and lots of samples, you know, will fall anywhere along this number line. Most of them will fall in the red region, 95% of them. So you might get a sample mean that falls there, or there, or there, or there, or here, right? 95% of the time they will fall in the red region. Okay, understand you don't know what mu is. Mu is the truth, and the truth is something we usually don't know. Okay? Just because we don't know it doesn't mean it doesn't exist. Yeah. The mu is definitely there, and this x bar falls within 2 standard deviations of the truth 95% of the time. Now, let me demonstrate that. Poof, like magic. Here's the thing I demonstrated in class. So if you were there, you've seen it. If you weren't there, then you haven't seen this, and it's a good thing you're watching this. I'm reproducing the experiment we did in the computer lab, taking random numbers between 0 and 99, sample size of 25. Okay, you guys took sample sizes of 100. We're going to do 25 instead. The population mean is 49.5. Trust me, it is. The population standard deviation is 28.87. Okay, and I'm going to circle those. That's mu. This is sigma. Okay? I'm going to leave my confidence level at 95% for now, and I'm going to generate 100 samples of size 25, and I'm going to create 100 confidence intervals around those x bars. Look at what we get. Here's 100 confidence intervals. Most of them capture the truth. Here's the truth right here. Notice how the truth doesn't change from sample to sample. It's the samples that change. Okay, the ones that are in red, this one, this one, this one, this one, did not capture the truth. We'd expect that. In fact, what we would expect is 95% of the time, the confidence interval we generate captures the truth. The other 5% of the time, it doesn't. And if I keep generating random samples, it's kind of slow because I'm running this video thing too. You'll notice that this approaches 95%, which is what it's supposed to. Okay? Cool. Let's take our sample size and make it bigger. What do you know about a statistic when we make its sample size bigger? Think about that. That's right. The statistic gets better at estimating the population parameter it's trying to estimate. If the statistic does a better job at estimating that true value, that truth, your confidence intervals don't have to be as wide. In order to have the same level of confidence, we don't need an interval that's as big as the one we've got right there. Let's generate 100 of those with a sample size of 100 and watch what happens. See how those intervals shrink way down? Yeah, they don't have to be as big because the statistic is a lot better than it used to be. Okay? Now let me bring this back to 25, where it was before. Alright, now 26, good enough. Let's generate 100 intervals like we had before. Let's take our confidence level and increase it from 95 to 99. What's going to happen to the width of my interval? That's right, it's going to get bigger. In order to be more confident of capturing the truth, I have to have a bigger interval to do it. And if you notice, my interval gets a lot bigger because now almost all of them are going to capture the truth. And that, in a nutshell, is how confidence intervals work. So, there you go. I hope that helps, and we'll see you later.